So this is a paper that I reviewed a little bit ago, but I didn't like the initial recording. So if you saw that one before, I basically changing it to be a little bit. There were a few things I described that I just didn't. I thought I described terribly. So hopefully it's better this time. Anyways, so hardware efficient attention for fast decoding is a cool paper. You got Tri down there, so you know it's going to be pretty cool paper. But basically, it's saying we have these forms of attention, and they are you have two different sides of why computations are slow. You have something that is memory bound, which means it takes longer to load stuff from memory and move it to SRAM in the GPU, from HBM to SRAM, than it does to do the actual computation. And that's kind of bad. Or you have things that are arithmetic bound, like computation bound, and that means that the memory movement isn't as is slower or is faster than doing the actual computation itself. So yeah, I'm going to be going over. I've drawn out some diagrams and just go over this with starting from normal attention and kind of building up from there with group query attention, and then with the additions they have to basically make this thing faster. So, and then I'll go through the results in their paper. But yeah, let me just start going through all these diagrams. So, good old normal attention, it kind of looks like, actually this is going to be for decode, but let's just go through this for normal attention. So like during training, you have, say, a sequence of tokens here. This will be maybe of size, I think I use t as the time dimension. Sometimes I use n, but basically this will be your input. You project this to your queries, keys, and values, which are going to be roughly of shape t by d, t by d, and t by d. Where these are your queries, these are your keys, and these are your values. And I'm going to add multiple heads in a second, but basically the main part of the computation, the thing that's slow, is this QK transpose here, and this is not memory bound. This is very much compute bound, because the stuff you have to move from HBM to SRAM, which is the memory, which is what could make things memory bound, is not that much compared to doing this big computation here, where this is your t by t quadratic matrix. And there are things to make this faster, like flash attention. So if I have, say, this is a causal mask, which in this case it is going to be causal, we're going to be working with causal mechanisms, because I'll talk about that in a second. But basically, if this is causal, you can use something like flash attention, and it's still computation bound. So it takes much longer to do the computation than it does to load your QK and V weight matrices from memory. And then you do your value projection here to get your outputs, and then you do your output head projection. So this is just normal attention, very much compute bound. Now, if we take this and we say, all right, so we have a pre-trained model, let's do inference on it. So for inference, there's two stages. That's a G. There's two stages. There's one, which is your prefill stage, and there's two, which is your decode stage. So if I'm a user and I have a prompt, say, what is 7 plus 2? Very, very difficult prompt. LLM may or may not get this right, but let's treat this as, say, 5 tokens. So it'd be 1, 2, 3, 4, and 5. And basically this is going to be a matrix of size t is equal to 5 by d. So whenever we get to the actual attention part, we're going to project this to our query keys and values, q, k, and v. And like I said, this is going to be working with, this is not going to be working with bidirectional LLMs or bidirectional models. It's just going to be causal models. So in the causal case, you have prefill, but if you have a bidirectional model, you don't have any prefill. And in the prefill stage, what you do is you're basically computing your keys and values for every part in your model. And the reason you do that is because basically for every token in your sequence, you can store the keys and values because the keys and values are causal. And basically the keys and values are what are sending information to to whatever this last token is, so that this last token can make the next prediction. So basically you compute the keys and values for all of your tokens in your, or for all the words in here, all at the same time. So this is a single forward pass through your model, computing all the keys and values. And you also compute the queries, so you're basically doing full normal attention like you would during training. It's just instead of throwing away everything during training, and instead of actually training the model, as you do a forward pass, you collect the keys and values into this thing called the KV cache. And this is what is called prefill. And it's prefill because you have your prompt here, you have the full prompt, and you just send this through the model at one time, and you get all the keys and values for all the parts of your initial prompt. So this is the prefill stage. This is compute bound because it's very, very similar to training, except you aren't doing back propagation. You're just doing forward passes to store your keys and values, where you just store the keys and values into a KV cache. And the reason this is compute bound is because you're still computing your big T by T matrix or doing your flash attention, so it's compute bound. You're doing this big computation. Now, whenever you get to the decode stage, you have your keys and values for all previous tokens in your prompt. So if we have what is 7 plus 2, you have your KV cache for all of these tokens here. What is 7 plus? And then you want to have, I guess you could also have it for the for 2 as well. In the example I have it just for these tokens here. But whatever. So for token 2, let's say we want to predict the next word for this. Maybe it'll give us an equals or something like that. But we're decoding. We want the model to make a prediction on this token. What we're going to do is we're going to take the token. We're going to project this to our keys, queries, and values. And what we're going to do is we're going to add the keys and values to our KV cache. So these keys and values here represent the keys and values for the prompt, what is 7 plus? And this extra token here is the token for 2. And this query here represents the token 2. So then what you do is you do your normal attention computation, except your attention computation is just going to be a vector, where your vector is, so this will be a 1 by t dimensional vector, and this will be your qk transpose, where q is a single vector, while k, so this will just be of dimension 1 by d, and k is of dimension d by t, where t in our case is equal to 5. And this represents all of the past keys. And then you do softmax to that, and then you multiply this by the values, where your values are t by d, where t is, again, all your past values, including the new value we added 2. So this is the decode stage. And the decode stage is memory bound, because what you have to do is you have to load these big, in this case, they're not real large, but imagine I'm prompting GPT, I go off, I talk to it, and it goes to like 10,000 tokens or whatever. I forget, I don't know, I think it's 32,000 or something like that for the context right now. Let's say I get to 10,000 tokens. That means there are 10,000 tokens it has to load from memory just to do a single vector multiplication. And that is very much memory bound. So it's really, really slow to load the KV caches from memory because this computation is so fast. It's just a vector times this matrix here. And real quick, what this represents, so if I have my attention matrix here, which is causal, again, we're working in the causal case. So this would be our keys and values, queries. It represents this last part of the matrix here. So that's where this vector is coming from. It's basically this last vector here, where this query represents the query for the token we want to decode, and the keys and values are all keys and values here. So that's what this is representing. Just wanted to mention that. So to add on top of that, we actually do multi-head attention, and multi-head attention, it kind of makes this problem worse. Unless d is equal to the number of heads by the head dimension, then it's the same problem. But Anyways, this isn't how we do attention. This is how we do attention, where this is just the same diagram, except I'm just adding multiple heads, and I'm adding multiple heads now just because we're going to remove them in a second. So multi-head attention is just normal attention we all know and love with multiple heads. If you've worked with attention, this is what you would usually see. So basically our input here is projected to not just one vector, but to h vectors of dimension dh instead of just d. So our KV caches are actually h KV caches, where h is the number of heads. And the attention scores we compute are actually h attention scores rather than just one vector. But this is very much memory bound because now we're loading h KV caches from memory. So yeah, this is a problem. So if this is how we're doing attention, which is how we normally do attention, how can we solve this problem? So in this paper, this is not what they propose. They propose how to make this better, but what this has been a thing for a number of years is first multi-query attention. Multi-query attention is basically saying, all right, so we have h heads, so this is how we normally do attention. Up here is not, this is just so I could talk about prefill and decode stages. What if we remove all the heads, and what if we just have one head? So what we're going to do is we're going to say, okay, so the problem is our KV cache. The problem is loading the KV cache from memory. It's not doing this computation over here. This computation is fast. It's loading the KV cache from HBM to SRAM on the GPU. So if that's the slow part, then why don't we just remove all h heads from our keys and values, but keep them in our queries? So this is what's called multi-query attention. For our input, instead of projecting our input to h keys, h values, and h queries, we're only going to project it to one key, one value, and one query. Or not one query, and h queries. Then what that means is your KV cache is reduced by a factor of h. So that means it's going to be on the order of h times faster to load this from memory, which is significantly faster because your KV cache can be, or the number of heads can be 16 or 32. So this significantly can reduce the number of keys and values you're loading from memory. Then what you do is you load your keys and values from memory, and basically you duplicate them h times. So load it from memory, and then you duplicate h times, or you do the computation in a smart way where you're not duplicating it h times, but essentially it's duplicating it h times and then doing the computation, where every key and value goes to every head here. So in this case up here, multi-head attention, the first key and value went with the first query, and the second key and value went with the second query. Now in this case, it's the first key and value go to the first query, the first key and value go to the second query, and so on. So it's one head goes to all heads here, which is just basically duplicating the head, however many, or duplicating the one key and value head for all the heads in the query. So this is a lot faster. It's a lot faster to load from memory, and there are this is a lot faster to load from HBM to SRAM, and it is less memory bound, which means it is going to be a lot faster to do your decoding in a transformer, which is what we all do today for inference. It's the slow part of inference. So what are the problems with this? One, we just reduced our keys and values by a factor of h, so it's going to be less expressive, theoretically, because we have a dimension we basically have it's a lot smaller of a dimension that we're working with by a factor of h. So reducing it by that much is quite a significant amount, but also it is not parallelizable. So there are kind of two problems they want to solve in this paper. One is parallelism, and two is speed. So this solves the speed problem, or rather it makes the speed problem better. So it's fast to load from memory, but it sucks at parallelism. For example, let's say we're doing decode with two GPUs. So we have GPU 1 and GPU 2. And we have our h heads here for our queries. So for our query heads, This is easy. We're going to take half of our query heads, and we're going to put them on GPU1, and we're going to take half of our query heads, and we're going to put them on GPU2. Now, the problem for our keys and values is we only have one head. That means we have to duplicate this for GPU1 and GPU2. But if we had two key and value heads, we could just put the first key and value head on GPU1 and the second key and value head on GPU2. And that'll be just as fast as if we duplicated one head twice. So we can basically grow the number of key and value heads by the number of GPUs we have. And there are two things group query attention solves. So group query attention is the next thing, is kind of a middle ground between multi-head attention and MQA. And the first thing it kind of improves upon is saying, well, only one head is kind of restrictive. What if we have multiple heads? So not H heads, but we have, if we have HQ, number of query heads, we'll have HKV, number of key value heads, where HQ is divisible by HKV. So maybe this is like 8 and this is 2. So this is some factor of this here. And also, if you make this value, or if you make the number of GPUs a factor of this, then you're basically getting free compute. So if we just had one GPU, then it wouldn't really matter. But if we had, say, 4 GPUs, then let's say we make this 8 and this 4, and we had 4 GPUs, this is essentially as fast as if you only had one key and value head and you duplicated it 4 times. It's the same memory movement that you have, essentially. So those are the two things it kind of helps with. It's more parameters, which is always better. We love more parameters. The more parameters, the better. But it also makes it more parallelizable because you don't duplicate your keys and values by the number of GPUs you have. You can just shard the number of keys and values by the number of GPUs you have instead, which is much more parameter GPU efficient. So what does this look like? It looks like something in the middle. So basically, like I explained above, you project your input to the number of query heads you have, and to or queries by the number of query heads you have, and keys and values by the number of keys and values you have, key and value heads you have. And like I mentioned before, HQ should be divisible by HKV. So maybe this is like 8 and 2, or 8 and 4, or 8 and 8 if you really wanted, which wouldn't have any saving, and that would just be MHA. But yeah, this is group query attention. So yeah, it improves upon the two things I said above. And basically, in this case, we have 2 and 4, where every key goes to 2 queries, as you can see here. The first key goes to the first 2 queries, and the second key goes to the second 2 queries, and it's the same for the values. The first value goes to the first 2 queries, and the second value goes to the second 2 queries. So you duplicate the number of keys and values by however many you need to get the number of query heads. So, can we make this better? The answer is yes. So if you have seen DeepSeek, and you've seen the MLA method they have, that basically said that they're kind of combining the MLA method from DeepSeek with this group query attention method here. And this is the first thing they propose. They propose something called group tied attention. So what group tied attention does is it says, all right, there's one more thing we can do, or there's another thing we can do to make this more parameter, or to make this more memory, to make this less memory bound. What we can do is we can take the keys and values. So right now we have a key and value matrix here for our KV cache. Instead, what we can do is say, what if these are the same things? What if instead of having 2 KV, a cache for our keys and a cache for our values? So I think if I write out the dimensions, this will be better. So this is T by D and this is T by D. So this is just normal group query attention where you have, I guess I should also add the number of heads. So this will be H by T by D for each matrix here. There. H by T by D for your keys and H by T by D for your values. what if instead we had one matrix that was h by t by d that stored both the keys and the values? So basically what we're saying is the keys and the values are the same thing. So this is basically merging they call this tied, or they don't call this tied, but this is called tying your keys and values together. So tied keys and values, where your keys and values are the same matrix, essentially. So that's what they say here. They say, what if we just tie the keys and values? What if we tie the keys and values together? And if you do that, then you reduce the size of your cache by 2. And that means that loading from memory is about twice as fast. It's not quite twice as fast, but it's theoretically twice as fast. It's you decrease by a factor of 2. Now there is a problem. The problem is if we have rope, we have to apply it to our keys somehow. But since our keys and our values are the same, you can't really just say, well, I just want to apply it to the keys, because the keys and values are the same. So the first idea is saying, well, what if we just apply a rope to our keys and our values? So we just apply it to both of them. And you store that in the cache. So every time you store your keys and values in the cache, your tied KV in the cache, you just apply rope like you would normally, and you just store that. And that would mean you're not only rotating the keys, but you're rotating the values as well. And the problem with that is rotating the keys makes sense. That is what rope is meant to do. But rotating the values, you're just kind of rotating the values arbitrarily by some position in you're just rotating the values arbitrarily. And the thought is maybe that doesn't matter, but it actually makes the model worse if you do that. So that's a problem. To fix this, they basically decouple this and the rope embedding. So instead of applying rope to the keys, you do this trick, and I'll show you the trick. So what we're going to do is we're going to take our input, the query's exactly the same, and over here is all exactly the same, where you do your matrix multiplication with the keys and values and so on. So don't worry about this side. This side's basically the same. This side over here is different. You take your input and you project this to one vector. So before we projected this to 2 vectors, our keys and our values vector. But now what we're going to do is project this to a single vector, which is the tied key and value vector. So now our KV cache is half the size, where we only have one vector that we're throwing in our KV cache. Then that's nice, because now all we have to do is load this one matrix from we just have to load this one matrix, which is really fast. Well, it's twice as fast as before, about. So you load in this matrix. Now, as I mentioned before, we have this problem of rotating the keys and values. So the first idea is, what if we just don't worry about that? So you could just copy your keys and values and do attention like normal. However, that is just bad. So instead what we're going to do is we're going to take our KV cache and we're going to copy it to produce the values. So our values are just our keys and values. It's just the same thing. You're literally just copy and pasting this, and that represents our values. Now our our keys are slightly different. What you're going to do is you're going to take the first half of your matrix here, and you're going to copy it. So that means that the first half of the values and the first half of the keys are the same. Now what I mentioned before is you need this rope information, and the rope information is decoupled. So what we're going to do is we're going to make the smallest vector that we can so that we still have this speed gain from storing a small amount of stuff in memory, but still getting this rope information. So to do that, we're going to add another projection, which gives us this really small vector of size dh by 1 head. So this is hkv, normal group query attention. This right here is going to be 1 head by a half dimension. And what we're going to do is we're going to store this in our KV cache. So we have our key value cache, our tied key value cache, and we also have our rope cache. And this here adds a little bit more to your memory, but not a ton. So this will be of size t by half dimension by h. So it's nearly half, but it's a little less than that you're gaining, because you have to store this as well. But what you do with this is you concatenate this rope embedding to the key and value embedding here. So remember, we took the first half of the keys and values. We have that here. And the second half will be this, this K rope thing, and we apply that here. And note that we have HKV heads here, and we have one head here. You basically duplicate this vector here by HKV times. So we have one, this is basically the smallest vector you can make that can add the rope information. I guess you can also decrease DH, and that would be interesting, or like how much of this takes up. They divide this in half, but maybe you could make this a third instead. But anyways, basically your values are just your keys and values, and your keys are the first half of the KV cache, and the second half is this rope embedding. And I think I've added enough circles. So yeah, that's the idea. And what this gives you is it gives you speed up from your group query attention by, because of the HKV is less than HQ. So HKV is less than HQ. That's the speed up you got from before, from group query attention. And you also have parallelism. Parallelism because of your, because you can distribute this across multiple GPUs because of HKV. And now you get a second speed up by about a factor of 2 because you tie your keys and values together. So yeah, this is what they call GTA, group tied attention. And this is the first thing they propose. Basically, you want this thing to be about as good as attention, but to be a lot faster. And we'll see it is later. So now, switching gears, the second thing that they propose is a modification on MLA. So MLA is this multi-head latent attention from DeepSeek. So it's a modification on that. First, let me kind of go through MLA, and talk about that. I basically want to talk about how you get to the equation they have over here. First, I should probably show the diagram they have. So if we look here, this is group query attention. This is multi-query attention. So basically, these are your queries, and you have your keys and values going to multiple queries. So group query attention, multi-query attention is you have one set of keys and values that do that. And group tied attention over here is basically saying it's the same as group query attention, except our keys and our values are going to be broken up into pieces where, yeah, you tie them together. So you're tying your keys and values together where the first part of, I think these are queries, or keys, where the first part of the keys are the same as the first part of the values, but the second part comes from your rope embedding here. So that's what this diagram's saying over here. But going on, there's this over here. So where does this come from? So there's this mess of matrices that are involved in GQ or in MLA. And what this gives you is this gives you a nice way to do inference. It's just kind of disgusting to look at. So you have all of these here, and I'm just going to go through it really quickly. But if you're curious, I think I have the right. Basically, you're absorbing matrices together during inference. That's the goal. So during training, you have these low rank projections, and the goal is to basically make a KV cache that isn't only, or that's smaller along the dimension index. So your KV cache here is going to be of size T by D. It's what if we have a tied KV cache that's also small on D. So that's what we're going to have here. So the important thing is just saying, I guess, what this looks like during inference. So I'll go through that. So this is our normal attention equation at time t. So our output at time t is equal to the queries multiplied by the keys multiplied by the values. And of course you have your softmax in here. I'm not adding extra things like the dimension, like division by the dimension and stuff. But you not only have that, you also have your output projection here along with the number of heads. So I'm kind of abusing notation and saying the output is equal to the concatenation of all of the head outputs multiplied by the weight matrix, the output weight matrix. Here, I'm just expanding it. And yeah, I'm using notation by just putting cat here so that I don't have to write this h times. And then here, I am expanding it a little bit more. So up here, we have, right here, we have Q and K. And Q and K are the concatenation of the queries and this rope embedding for the queries. And the reason we have these two embeddings is so we don't run into the problem up here, where if we tied, or whenever we tie the keys and values together, you run into the problem where you have to rotate the values. While here, if you decouple the rope embedding from the key embedding, then you don't run into that problem. So that's what we're doing here. We're breaking it up into a key embedding and a rope embedding for the keys, and you do the same for the queries. So here, I'm breaking it up one more time. Basically, you have this matrix multiplication here that you're doing. So I'm just translating this concatenation over here into these two concatenations right here. And this is just using all the equations above up here that define the MLA. And this is the same thing, essentially. And then I'm also breaking up the values. And basically, what you have is you have your hidden states are defining your queries, while you have this C matrix here, which is what you're actually going to store, that defines your keys and values. So then this here is me basically highlighting that you can merge these matrices together, this WDQ and WUQ, and these matrices here, to get a WQ and a WVK matrix. Then finally, you have this step here, which combines these two matrices here. Because this is an inner product, you can just combine these matrices. And this will be the matrix that we're using during inference. And during inference, you basically store three matrices here, or two matrices. You store this one here, this C1 to T KV, which is basically a tied KV cache. And this rope here, which is essentially the rope vector, this rope cache that you're storing that we had above. And yeah, this is the same here as this one right here. It's just kind of duplicated, where this one is for the keys and this one's for the values. Then, yeah, so during your cache is these two matrices here. And then during inference, you're basically going to use this formula over here. Where, you're going to use this formula over here, where the queries come from this projection right here. Same for the rope. So yeah, this is just quick me going through how you would get to the inference procedure, but all that to say, you're storing these two matrices here. This tied KV and this rope, this rope piece that's not part of that matrix. So what does this look like? To make this look a little bit better instead of this mess up here, it looks very similar to what we had above. Basically, you have your input here, your hidden values at time t. You project this to 1, your C vector, and the C vector is going to be, you have DC here, where DC is going to be 1/4 of your head dimension here. So this is kind of like down projecting in a way, and this is going to represent your keys and values. So not only do you have your keys and values, which are, in this case, it's one head, you have a half, or you have keys and values are stored together, so tied, but you also have a small dimension. So this is the third axis they're kind of changing. They're saying, let's decrease the dimension to reduce the KV cache even more. So this is the third axis that's kind of being scaled to decrease to make it less memory bottlenecked. And then of course you have your rope part here. So during inference, whenever you load this from memory, you load the keys or you load this KV cache, which is the C memory from memory, which is your tied KV cache, and you're just going to copy and paste this over to your values, and you're going to concatenate essentially this along with your key vector or your key rope vector to do your attention computation here. So it's very, very similar to what we had above to GTA, except we're also reducing the dimension, and except we only have one head. And you may notice that that's a problem. We only have one head, and this is the same thing that you see with MQA, I think it was, whatever the first thing was where you only have one head. It's the same problem that you have with that. This isn't parallelizable, and you can basically get free parameters if you do inference with multiple GPUs. So what they propose is they say, if this is the same problem as what we had above, and we can just add a few more heads, then why don't we just do that? So that's the final optimization. So this is from DeepSeek up here. They say, what if you just add a few more heads? So it's the same exact idea. It's saying if we have HQ, and instead of just having one head and for HKV, instead we can make HQ divisible by HKV, where HKV is some value greater than that. So maybe this is 8, this is 4, and if we have 4 GPUs, this is just as good as if it was one head, except now we have multiple heads, the model can do a little bit better. So that's the idea up here. It's saying, well, let's just take the MLA architecture and let's just add a couple more heads, just like we did above with multi-query attention. And this is just so that you can make it more parallelizable, but also a little bit better in terms of accuracy. So how well do all of these do? This is just a bunch of attention architectures, but how well do they do? So if we look at it, it looks like MLA and GLA seem to do the best. GLA seems to do quite well. It seems to do the best overall. And GLA, again, is the optimization on MLA, where MLA comes from DeepSeek. So it seems to do pretty well. And if we look here, it seems like it's the winner is GLA again. And here, it looks like MLA or GLA. This one's kind of mixed here. This one, it's definitely GTA that's better. And GTA was the first proposition they had, and then GQA. So it seems to be kind of a mix between the two propositions they have for how well it does in terms of accuracy. Now, how well does this do in terms of speed? So if we're trying to optimize this for speed via parallelization, let's check out how fast it is. So here is Flash MLA, and their proposition is GLA, and they show it's really, really fast, comparatively speaking. And this is for decode. So this is not the prefill stage, this is the decode stage, and it does a lot faster. It's a lot faster in terms of speed here. I think they show the same thing here. And in this case, they have TP is equal to 8, so they're using 8 GPUs to do decode. So they're parallelizing this across 8 GPUs, and they show GLA is quite a bit faster than MLA. They also show here for prefill, it is a little bit faster here. And for, I think this is also prefill. I think this is decode. For floating point 8, it's much faster for decode. Their proposition of GLA. So just adding a few more heads seems to be a lot better in terms of speed, and a little bit better in terms of accuracy. But yeah, that is the paper. It's basically saying there are redundancies, like there are things you can do to optimize your computations such that they go with the hardware rather than just creating architectures that look good. So it's saying instead of just creating an architecture that just works because machine learning, you should also think about how, like, what is this thing running on? Right now it's GPUs, but it could be something else in the future. Right now we have GPUs. And if you can make an architecture that is really good for utilizing GPUs, then you can make something that is not only good, but is also really fast. And it's kind of baking in the hardware that you're using into these mechanisms that you're creating and working with. And that can make training and inference a lot faster and a lot cheaper. So yeah, that is this paper, Hardware Efficient Attention for Fast Decoding. Yeah, I think it's pretty cool that it's just baking in the hardware into the architectures. And yeah, I'm curious to see if these are actually adopted in the future.